Good morning, everyone. My name is Sumun, and it's a great pleasure to be back in Bangalore after 7 years. My first visit to Bangalore was for COMSNETS 2010, and it was in the same hotel. At the time, it was my first visit to Bangalore. It was a great time. Microsoft research was not just around the corner, it was far away. I went to the restaurant Caravali last time. I went there last night again. Same old, very great food. But last time, I didn't check out the lunch house next door. But this time, it's the best fish restaurant for me so far. And I think I'm going to visit there a couple more times before I head home. All right. It's a great pleasure to give this talk. As Sergey mentioned, that my research areas, I have two main research areas. One is on online social media. The other is networking platforms. They're very different topics. And I really struggle to keep up with research in both topics. Luckily, I've been privileged to work with really best students I could ever imagine to have, so managed to do in both fields. The social networking, online social media work, the current push, we just wrote up a proposal, and it just makes my heart beat. So, and we haven't done anything, but I'm making my enticing my students to get involved, but we're pulled together a 3-page proposal. It's about pulling HCI, crowdsourcing technology, IT, and social scientists to work together, that we're going to provide a platform for 21st century democracy. I think every country today is experiencing a great change in the political scene. And I think we could help out by making the data that we have, government data, any statistics from the census, having the data available and getting the public engaged, and so that we can change the 21st century into a more modern democracy based on modern tools, not on strictly online, strictly voting system. And today I'm going to talk about the networking platform issues, and it's an opportunity. This talk is an opportunity for me to go over what I've done so far and what I will be doing. And my views, my perspective on the technology advances is very biased, but I think you want a biased view so that you can disagree, and I think that'll make it a lot more entertaining. All right, so I'd like to start with the telecommunication network world that I was born into. So the world of telecoms, I think there are half of the crowd, half of the audience here are students, and students are not familiar with some of the companies because they are old and they are no longer in the textbooks. Okay, AT&T Mabel before the 1986, British Telecom, France Telecom, Deutsche Telekom in Europe and Americas, and Korea Telecom, China Telecom. I looked it up on the Wikipedia, and I think it was Indian telephone industry as a set. And then you have NTT, which stands for Nippon Telegraph and Telephone. And I don't think most of the students here haven't even tried a telegraph or received any telegraph. Okay, that was old. Okay. Now, today's networking world, mostly mobile operators, cellular phone. In US, Verizon and AT&T. In Britain, it's EE or O2. France, Orange, Deutsche Telekom. In Germany, O2. In Korea, we have SK Broadband, which serves more than half of the Korean population with high-speed interconnection, high-speed internet connection, and cell phone service. And China Telecom still. And in India, I just looked up, and Airtel is the #1 service provider. And in Japan, it's NTT Docomo and KDDI. So the market has changed greatly. Okay, and the IP traffic by devices. How are we using the network? How are we using the network? It's just some market number from Cisco. And the points to take from this slide are, first, the traffic is going to double, almost double, more than double from 2015 to 2020. And most traffic will come first from PCs, smartphones, and TVs. Okay, so you can tell smartphones and TVs basically take up more or less the same amount of traffic, meaning that it'll be mostly video. Okay, so there's been a lot of change in the market, in the traffic patterns at all, but in the computer network textbook, you learn TCP/IP. You got rid of BitNet, DECnet, SNA, the old protocols. The only thing you learn is TCP/IP. And what has changed? Not much has changed. There isn't much research to do because we still have the same old TCP/IP. You just use TCP/IP everywhere and you're all set. No. There are a lot of interesting things to do in networking, and that's how I'd like to motivate you. So this is how I see the network core in the old telecom words and also in today's words. So we have a core router at the top, which is the most expensive gear. That would be, if you have it fully furbished, then the core router itself will be, say, almost $1 million, okay? And then you have, and why might sell it for half the price or even a third of the price, okay? And then you have access routers, and access routers are the aggregation point of high-speed switches. And I've added these pink boxes called middle boxes, and I'll get back to these middle boxes later, okay, again. And then, what are these middle boxes? So these middle boxes, there are a variety of middle boxes: firewalls, monitors, accelerators, intrusion detection system, deep packet inspection, and then load balancers, DOS protection, and also add insertion boxes. Okay, so all these extra boxes, they look similar, different, but these are also basically computers. And at the edge, still, I am basically using the same configuration, but they are slightly different. This is basically a router configuration that you'd have. I'm not going to move, okay? I'm just going to be using my hands, okay? So we have a router, gateway router, and then switches, and then you're going to have lots of hosts attached to a switch. So this would be a typical configuration at any small enterprise, small, medium-sized enterprises and universities, okay? And now we have data center networking. Just bear with me why I'm introducing data center networking in the middle now. We'll come back here. Data center networking router, you have routers, and then at top of rack switch, and then you have lots of hosts. And here, the middle boxes are on the hosts, okay? So at the edge network, you have middle boxes attaching before or after gateway routers. And in the network core, depending on how you're partitioning the router, you have these middle boxes attached somewhere in the network core. And edge, you have usually near the gateway router, but then when you move on to the data center network, you don't know how you're going to partition the network. So you'll have to do, so what is a software router? I call it networking devices that are mostly built from commodity hardware. I'm calling mostly because not every component is going to be commodity. Commodity is not a hard definition. It all depends on the market. Custom hardware can be commodity if they are started to be mass produced. Okay, so why are we talking about software router in my today? First, I'm going to start with this. So this is the typical network in old days, or in big telecom networks, okay? So you can put these middle boxes anywhere, okay? And what are these middle boxes? These middle boxes are mostly custom hardware, okay? You build a high-end packet processing firewall, IDS. These boxes are all custom built or built from commodity hardware with added features, specifically for packet processing. Okay? And they were selling for a very high price. Yeah, cost cutting is great, and it can be a great research topic, but actually, high cost is not too bad for us engineers, because they create jobs and we get paid well. So expensive devices for networking researchers, great thing, because we get to charge a lot and make a lot of money. But come data center networking. In the data center networking, you have a router, you may have router, and top of rack switch. So who has seen pictures of data center networking? Yeah, you just see, it's just a huge soccer field or larger warehouse with just rows of racks of computers, and that's it, right? Uniform PC, 1U, 2U, 4U racks of computers, okay? There, you have no room for dedicated hardware, okay? You are just gonna use servers. So for all the middle boxes, I'm not going to go over. I'm not going to go back to the old slides. But the pictures that I've shown you of middle boxes, those dedicated hardwares have no room to go in data center networking. Okay? So you need to make all those functions, I call, or middle boxes, or we call network functions these days, come work in the data center networking without specific hardwares. So that's the challenge that we have in today with most of computing done in data center networking. And that's how I'm setting you for the rest of this talk. So what is a software router, and what does it have to do? So a router is a computer, whether you use PC or build a dedicated hardware, it is a computer, and you need to think about the computation power. So what do we need at software routers and switches? Let's think. At 1 gigabits per second, that means 10 to the 9th, and then let's assume that every packet is 64 bytes and times 8 bits, and you divide it by, and then you basically have about 2 packets per second. So if you want to process packets arriving at 1 gig, then you need 2 megabits per second. Okay. So on Intel Xeon E5 Sandy Bridge, it's an old one, but then you have 2.6 gigahertz cores, and you have 8 of them. And let's say you have dual, so 2. Then you have 31 gigahertz. That means you have 31 gigacycles, right? Or let's say you divide it by 2 mega packets per second. That means about 15K cycles per packet. Okay? Then if you multiply, so that was for a 1 gigabits per second link. If you upgrade it to 10 gigabits per second, then you're going to need about 10 times more cycles per packet. Right? So the number of cycles you need for a link that is 10 times faster, you just need 10 times more cycles. Okay? So let's do a little more math. You have 40 gigabits per second, then you're going to have about 375 cycles per packet. Okay. That's very, very tight. Now you come to think of it. Okay, 31 gigahertz is very nice, but very few instruction, CPU instruction, is done in one cycle, right? They are heavily pipelined. Any memory access is going to cost at least tens of cycles or hundreds of cycles. So to run a 40 gigabits per second line rate with commodity CPU processors without any extra help, you have very tight CPU cycle. And this is going to be always there, okay? Because CPU cycles are not getting faster, right? But network speed is getting very fast, okay? So here, I come from a very wired country, and my brother, so I get 1 gig Ethernet at home. So I usually enjoy hundreds of megabits per second at home and at work as well. And US 4G, some parts 4G, and some high speed. But my brother, who lives in San Jose, was shocked to get hundreds of download and upload speed at my place last week. And now I'm in India, 3G, and 2 orders of magnitude or even less. It took me 30 minutes to download a 10 megabyte size file for my daily news. And so we have very wide range of speeds to cover in the world, but the network core is getting very fast. Data centers around the world, they're getting very fast. So 5 years ago, I think about 10 years ago, the data centers were still using 100 megabits per second per PC, and they upgraded to 1G. Now they're all up to 10G, and some are going to 40G. So every server in the data center network is operating at 10G Ethernet speed. Okay? So meaning that they will have under this configuration, about 1,500 cycles per packet, and that's very limited, okay? So, per packet CPU cycles for 10G. So, we did some number. This is an old number, but IPv4, IPv6, IPsec, depending on what protocol, the number of cycles that we need. We actually run basically the Linux code and then did profiling. And then for any IPv4, V6, IPsec, no matter what, for basic packet I/O, meaning to pull the packet from the Ethernet to bring it to the CPU, and then do the protocol-specific processing. For packet I/O, it needs 1,200 cycles. And for IPv4, we need 600 cycles. IPv6, we need 1,000 more cycles to do IPv4 lookup than IPv4 lookup. And IPsec, we just need an order of magnitude greater number of cycles. Okay. Then at 10G, we only had 1,500 cycles. So that means we could not do anything as is, say 10 years ago with the Linux kernel. Okay. So what can we do? And what can we do? This is, you have to pay attention. In the hardware, you have 100 meg Ethernet to 1G Ethernet, 1G Ethernet to 10G Ethernet, and 10G Ethernet to 100G Ethernet. In the networking cores, or edge networks, the routers will deliver the line rate. If we say 100 to 1G, the routers will deliver 100 to 1G. 1G to 10G, the routers and line cards will deliver 1G to 10G. But software routers, or PC-based routers, commodity hardware-based software routers, could not deliver immediately the increase, an order of magnitude increase in the line rate. So here, from 2000 to 2015, in 2003, we got first introduction of 10G Ethernet commercial, and people could buy it. Okay. But then it was only 2009. In route bricks, they could deliver 8.5 gigabits per second out of single box. And they put 4 boxes together and could get more than 10G speed of commodity hardware. And then it's only at 2010, our PacketShader, we could deliver 40G, single PC 40G bits per second. Okay. So it took how long? Almost a decade for a software for a software router to deliver the line rate that they need. Okay? And now Intel is delivering their own 10G driver framework. So Intel and Mellanox, these companies deliver 10G hardware, but they haven't been actually delivering 10G software. It's only with Intel's DPDK, they are delivering the matching software to pull 10G out of their own 10G hardware. And then now, in 2013, Kaku switch could do a single PC 80G. So far, out of single PC, I think 80G is the best performance we could get, but we'll have to try new architecture because there's a bottleneck at the bus speed, etc. Okay? So I'm going with a very high-level brief. So in the previous slides, we've seen that CPUs alone cannot give us enough cycles. So we need to get extra cycles. Where do we get extra cycles? We add accelerators. And the most common form of accelerator is a GPU, graphic cards that you use for online games. But not just for online games, scientific computation, and now we can do it for packet processing. So CPU versus GPU, GPU has been a fitting accelerator. Why? Okay, I should not say fitting. Okay, I should say good. Good. It's been a good accelerator because packet processing are somewhat repetitive and the same thing. You work on the header, you work on the TTL field, look at the IP addresses of the source and destination and the port numbers, etc. So you basically do more or less the same computation in all packets. So that fits very well to the utilization of GPUs. All right, so PacketShader PSIO. So in the previous slide that I showed, for IPv6, etc., IPv4, v6, and IPsec, we still need 1,200 cycles for packet I/O, and then we actually reduced it to 200 cycles per packet. So the main idea was to basically change the way the kernel deals with the packet. Okay, so instead of using per packet memory allocation, we just started with a huge packet buffer and removed the memory allocation and the allocation overhead. And instead of processing packets, every packet separately, we put all the packets, multiple packets in a single, say, batch, and then process packets in a batch instead of individually. That way, we cut down the interface time between the network interface card and the CPU. Okay? So that way, we could cut it down to 200 cycles, and we provided this new device driver called PSIO, which I think was an inspiration behind Intel's DPDK. And still, for IPv4, v6, and IPsec, we need extra computation. So here, we actually did offloading to GPU. So GPU offloading for memory-intensive or compute-intensive operation. Okay. So with this, we could deliver 40G out of a single box long time in 2010. But then, this PacketShader was not exactly a router. We tried to claim it was a router at that time, but it was not really a router. It was a patchwork of micro benchmarks. We twisted every code of line to deliver 80G. Okay, so when I asked a new student of mine to, hey, we got a new machine, can you set PacketShader up and basically reproduce the numbers? And it took him 6 months. Why? Because every line of code was hard-coded with constant numbers, and there was no flexibility. And so I asked my students to go open source, and there was this PSIO part and the GPU offloading part. And PSIO part, we actually made it open source, and I think a lot of you companies even benefited, but we could not make the GPU part open source, partly because we did follow-up work on SSL shader, and a lot of the IPsec code was reutilized, and so we had it open for a while, and then we took it off the web. But also, it was not a publishable quality code, as usual for most grad students. But at the same time, there was no flexibility in the coding, the design. It was just to demonstrate that you can pull this much performance out of a commodity hardware for high-end networking. Okay? So the next research was to build a more general framework so that people can do high-speed networking on commodity platforms. So we code-named it Smart Port Box. So it's basically the same idea of moving middle boxes in data network core, edge networks to data center networking. It's more or less high speed, but you have to move functions, network functions, middle box network functions from dedicated hardware to commodity hardware with the line speed. So today's router here has multi-purpose. These functions are either built in or added additionally with extra boxes in line in the fiber path, okay? And we wanted to push all that out to PC-based smart port boxes, individual boxes, and high-performance commodity switch. That is something, it's commodity, but not the kind of consumer-level commodity, okay? And for this is a more elaborate, more friendly, it's a repeat of what I showed in the skeletal diagram a few slides ago. It's a typical enterprise network, and this is where you have extra boxes like firewalls and extra middle boxes. So here, if we could have a smart port box, you'll have a very easy way of configuring a very high-end router with a high-speed bare bones switch and extra functions all into PCs. Okay? So how are you going to do horizontal scaling? Okay. Here, what's important here is that if you're going to add extra networking functions, instead of adding boxes, you're going to add CPU cycles. And how are you going to add CPU cycles? So here, there are many different ways of horizontal scaling. A is basically what Routbricks did in 2009 with 4 PCs, and then they're all interconnected, and every box basically doing the same. Okay, so it is scalable that you add more boxes and add more NICs. You can scale overall, but each PC has limited CPU, and there is no way to expand it. Okay, here B is somewhat similar to A, but you replace the switching with the switching fabric in the middle, B. So still, it is the same configuration as A. Each PC will basically do the same function, but instead of having multiple NIC cards per box, you delegate the switching to a real switch in the middle. Okay? This is similar to smart port. C is somewhat different. C is you have a switch, and at the back end you have lots of hosts, and then you're going to think about how much function you're going to add, how much cycles you're going to add to network functions versus the typical computing. So C is the most flexible configuration. Okay, and this is the E2 idea from Berkeley. Okay, so there are many horizontal scaling models. I'm going to come back to this model. So flexibility versus performance. We want flexibility, but we always lose out on performance. And I think this contrast, flexibility and performance, is going to be my challenge for the next 5 years, the same. So here on the x-axis, I put performance, and on the y-axis, I put flexibility. So here, Click Modular Router was a very old software router which boasted the most flexibility. You could build a router just by coding. Okay? And then RouteBricks was based on Click Modular Router, but and DoubleClick, Snap, these are all software routers with minor modifications to Click. But then why didn't PacketShader use Click Modular Router? Click Modular Router was introduced in 2000. It was before everybody had multi-core. It was before everybody had dual processors. So it was for a single-threaded machine, basically. So you had to expand that and basically make Click Modular Router adapt to the modern day computer architecture. And that was our goal to go on to NBA. So I'm going to go over what I'm going to talk about today. So our roadmap is getting 10G out of 10G port, which I think we covered. And then we want to build a general framework, not just hardcore numbers, but make it general enough so that people can build. And then augment computing power with accelerators. So we tried GPU, but there's a new competitor in the market called Intel Xeon. Okay? And at the time, we had Nike's Corner as a packet processor. And then when you scale horizontally with new interconnect technologies, we just by default assume Ethernet, but we thought maybe we could do RDMA over converged Ethernet, RC. Okay? And into the cloud. Now we're moving this software router into the cloud. What are the remaining challenges? And then we're doing something I'm gonna call funky. Who in this crowd is not a networking person? I'm a programming language person. Excellent, excellent. So any of you heard of type-safe language? Okay, yeah? Rust? Any of you heard Rust? All right, okay. So yeah, that's the thing. We're going to try using a different language for computer protocol implementation. The last two bullets are really ongoing. We don't have published work, but I hope my students are working very hard. And if you have any interesting ideas, etc., please do come. Okay. So the rest of the talk, I'm going to cover Networking Balancing Act, which was best student paper at URSS 15, and KNAP to be presented at HiPineB 2017, and this converge ROC versus Ethernet in HiPine 26, and also S6. So a little bit of it. Okay. So what is Network Balancing Act? So network packet processing requires balances between matching speed of I/O and computation, and flexibility for high performance hardware versus software, and workload distribution to multi-cores and heterogeneous processors. So NBA is a slogan towards a world where we do not need to manually balance them anymore. We have one framework that'll do the balancing between CPU above, and we are not going to trade off performance for the other. Okay. This was where our case. So flexibility prefers performance is NBA. So you basically think PacketShader was just for us to show you the numbers, and NBA is for you to try out the PacketShader speed. Okay. So this framework does not come with greatly novel ideas. Some people can try, oh, it's an engineering effort, boo. But to build a framework that works for everybody, it's a lot of work. The useful ideas that we took from existing work is it's modular, reusable abstraction for packet processing functions. It's a basic idea of click modular router. And multi-core scalable and NUMA support. It's any programming framework would need this, and GPU acceleration. Okay? So NBA delivers optimized and batched packet processing pipeline while preserving the per packet modular abstractions and new offloading abstractions for GPU so that you can use GPU without really worrying about how to do the offloading between CPU and GPU. And we do the adaptive load balancer. So when the traffic is low, you don't have to engage the GPU, you do the work in CPU. You don't have to use GPU all the time. There are downsides of using GPU. You need extra power to gear up GPU, and it takes time to send packets to the GPU and get it back, etc. So when the traffic at the 1 gigabit line speed, 10 gigabit line speed, if you're getting not 10 gigabit, but just 1 gigabit line speed, you don't have to engage GPU, right? So we'll do even the decision-making, load balancing decision-making within the framework, okay? So this is a high-level schema of NBA framework. We have NICs on the left, and then every NIC supports this queues, and then we have worker threads running at every core, and then you have actually extra dedicated device thread with GPU that'll basically do the handling with GPU on its own, and then the back. The high level is very okay. So packet I/O and multi-core structure implemented using Intel DPTK. So we had a choice of using our own PacketShader I/O, PSIO, or Intel's DPTK. So I'm a professor. I don't have a company. So when a grad student graduates, the device driver is not updated, and you have a new device card, new cards coming out, and the device driver doesn't work. I have no way to keep up with. So we made a strategic decision to drop PSIO and play along with the commercial offerings. So we chose Intel DPTK for later. And then this is workers. We basically take a lot of the common, design highlights of click modular router. But in click modular router, you have just single thread, but here we have multi-threads, and we're basically pin each thread to individual cores. So the packet processing pipeline, each pipeline will be pinned to an individual core, and then we'll have a dedicated thread for GPU interaction. You think maybe we have multiple cores, so every core can communicate with GPU, and that'll get better communication, better performance out of GPU. No, you actually dedicate a single core and have that core communicate with GPU alone. That way you actually get much better performance. Okay? So how NBA makes your life easier? I think they don't like this. So top-down example, it's this is what? So you have Q, and then you have to encrypt and do L2 forward and 2Q. So here, my encrypt, you just do the crypt and L2 forward. And this is how you used to do in click, okay? And this is, you still have to do the part, but the code has changed slightly. So we wanted to modify the existing public code that runs on click modular router, but it didn't really work. So we could not convert existing click modular router code automatically to our NBA. But still, the amount of work that you have to do is not very far. It's just that these click modular router, it's supposed to be modular, but it turns out to be, there are a lot of interchanging links among objects, etc. So it was not very clean cut as we wished. Anyway, so NBA gives you advantage to take care of multi-core architecture without you worrying about multi-core architecture, okay? And so inside NBA, we do a lot of batching, okay? Computation batching, you wrap process by for loop over a batch of input packets, and also use branch prediction technique to mitigate batch split problems, okay? All right, I'll be fast, okay? So simple branch prediction, you have majority path, minority path, depending on. So you basically do the computation for the majority path and do extra. Basically, majority path will be the fast path, and minority path would be the slow path. And if the packet is in the majority path, then you will have less of in the work. So here what we're showing is the baseline is no branch, it's the best throughput you can get. And then if the minority path ratio is only 1%, the red line, it shows that you have almost the same as like no branch. So you still have a little bit of overhead, but it's not too bad. And offloading to GPU, you have CPU, GPU, APU, and then you have to worry about you batch, pipeline, prepare buffers, host to device copy, launch GPU kernel, synchronize the results, and then device to host copy and dispatch. This will all take care of. So you will just do manage by the framework, and you basically write the code that's going to run on GPU, and the framework will take care of. Okay, so writing GPU elements in NBA, you specify devices, how the device should be copied, etc., and then write the code and register, etc. I'm gonna skip fast to NBA. Okay, and then we take advantage of data blocks. It's a high-level abstraction that cover common packet processing applications, and this matches very well with typical packet processing applications. Okay, benefits and this. So NBA is a public source, and you can go to GitHub and download it and play with it. I would like to hear whether NBA working on different platforms, on different PCs, they work, and it'd be best. I mean, you don't have to use the GPU part. The CPU alone part will basically work as much faster than using the typical click modular router. So if you are thinking about doing some graduate level networking course projects, then please take advantage of NBA and play with it. Okay. So KNAP. So Xeon Phi is cool. It's another accelerator that came from Intel. And in today's world's top 500 supercomputers, the #1 place is always a contention between GPU acceleration and Intel Xeon acceleration. I think in the past couple of years, I think it's Intel Xeon accelerators that's taking over the lead. Okay. So it is quite natural to think that Xeon Phi would be a suitable fit than a GPU. So Xeon CPU Phi configuration, how is it different? So you have CPU, and then you have Xeon Phi, and then you have this PCI Express. So you add a sort. One good thing about Intel Xeon Phi is you can just run vanilla Linux kernel on Xeon Phi and communicate. So it's basically more closer. It's GPU programming has a steep learning curve. Okay, it takes time, but Xeon Phi, you just run and compile the code, and it'll run, which is nice. But then why would you need an extra accelerator? It actually has a very different interconnect and very different hardware support for acceleration. And in this case, Xeon Phi is big on vectorized functions. Okay, so there are many different choices of offloading schemes, and we tried all this, and we tried multiple, and they are basically, we're gonna just go with POSIX threads, the very vanilla threads, instead of existing OpenCL, MP, Intel Click, Silk Plus, and TBB, right? And there are Intel Xeon Phi, the board that we have, had 64 cores. And how are we going to have the 4 cores work for us? Are we going to have all the cores do the same packet processing, or are we going to group them and then so we devised this abstraction called vDevice, which is grouping cores to multiple cores to a single computation abstraction, so that as vDevice we will allocate a workload, different workload. So with this and then the KNAP architecture is somewhat similar to the one that we've seen for NBA. Okay, and then IPv4 packet forwarding performance. IPv4 packet forwarding processing, we try it, but the best is just do it on CPU. Okay, IPv4 packet processing requires very minimal number of CPUs. So even though we try it, it's basically not worth crossing the PCI bus to Intel, Xeon Phi, or GPU. So we recommend just doing v4 on CPU, but it's still, what we're getting is not too bad. Okay, here, the RTT, if you pay attention to RTT, depending on the batch size, if the batch is too small, then the RTT is very large, but as the batch size grows to 512, it's the smallest. So this kind of batch size selection, you need to do micro benchmarking to select the best batch size, and this the framework takes care of. Okay, that's it. I'm gonna RDMA over converged Ethernet versus Ethernet. So who's tried RDMA? Okay, who works at a data center networking? Okay, so Microsoft, for example, is using RDMA for the communication between compute servers and storage servers. Okay, so it's very high speed, but it's basically over Ethernet, but still we thought, ROC is reporting very low latency. So in this case, we were thinking of strictly B, but instead of having the Ethernet switch in the middle, just using Ethernet in the middle, maybe we thought we could do ROC, okay? And this is what ROC looks like over DPDK. ROC has this scatter-gather function in their ROC LAN cards. So it's hardware-assisted scatter-gather. Why is it interesting? I said at the beginning of my talk, it's mostly commodity hardware. But today, the commodity hardware market is changing very fast. Okay, Google has about 1 million servers in their data centers around the world. When Google orders anything, it turns custom hardware into commodity technology because they order anything in such large number. Okay, so nowadays, I think the technology below IP. So you do IP, but how to do IP layer packet processing. There is a fierce fight between software versus hardware, etc. So Microsoft is adding FPGA cards, FPGA chips onto their networking cards to add any extra communication. I don't know how they're doing. Google Tensor is more or less the same approach. So it's commodities with a question mark technology that they're doing. And it's one of our approach, our trials of trying out a different hardware technology was RDAM. In essence, it's not too bad, but you need large packets. If you have small packets, the throughput drops dramatically. And so, in a way, this is like a negative result from networking research, but I thought somebody might be interested. So path forward, performance versus features. In the previous brief history, I had performance at the axis. At the y-axis, I had flexibility. Now I changed this graph with features on the top. Okay, so you will have flexibility. So NBA, we deliver flexibility. On top, we're going to see now how easy it's going to be to add features, apps. Okay, so the next one is S6. My student Shine, PhD student Shine, she's going to talk about this S6 in this afternoon's PhD forum. So I'm just going to have very high-level view here. So network functions in DCN. In the old days, you'd have a switch and network functions as separate boxes. Now, in the DCN, network functions are going to be added in this way. And if the network function requires a lot of CPU, then you're going to have, you might have just an extra box running VM, and then network function. So many different configurations. And the challenge here is horizontal scaling. So network function migration, virtualization, you think, oh, we know how to migrate virtual machines. What's the big deal of migrating network functions? Okay. So the thing is, network functions are stateful, and they require very high performance. So the requirements for network functions, migrations, are very different from virtual machine functions, and that's going to be the focus of Shine's talk. Rust first, rusted TCP stack. What is Rust? It's a language developed by Mozilla Foundation, and it's a very different constraints. You have linear type system, basically having one writer, and no one else can share. Okay, so it's a very strict way of doing programming, but you allocate and deallocate. There's going to be no memory leak, no error. Basically, you're going to get rid of most syntax errors in programming. So why haven't people tried type-safe language? Because it's slow, okay? Because you do a lot of the type checking in the compile time, etc. It's very slow, but Rust is hot because it's delivering performance. So I'm going to skip this part just to show you that we think we're getting compatible performance. So it's not up to there. But if you use PDK, we're trying Rust in all different ways. And let's say optimal, we get about 70–80% of DPDK, which I think is great enough. So one day you might be doing TCP, IP implementation, not in C, C++, in a type-safe language that you worry about. And especially in IoT devices, etc., where you have one TCP, one IP protocol that we survived for the past 50 years, but there are millions of implementations of TCP IP, and they are just so error-prone. Okay? So we hope this Rust is going to be a new approach to try networking programming. All right. I had a long list of past and present collaborators, and I hope I didn't miss anybody. And one last note, COMSNETS, a similar name, CONEX 2017. It's a ACM SIGCOMM conference. It's going to be in Seoul. It's going to be somewhere near or in Seoul. We're reviewing the hotel, quotes, this coming December. And I'll be co-chairing with Ted Kwan at Seoul National University. CONEX has come to Asia a couple of times. It came to Japan, but this major conference is coming to the region. I would like to have this conference benefit the greater Asian region. We're trying very hard, and we've already secured at least 20K for travel grants for students from the region. So I strongly encourage you to wait for the website to come up and apply for student travel grants. All right, sorry for running a bit over time, but I'm ready for questions.
Okay, let's thank Sue for the talk. And we're running a bit late, but maybe we have time for one or two questions.
Thanks, Sue. That was a great talk. So initially, you started off saying that there was, 375 cycles is all you have for packet processing and so forth. So when you go to some high-level languages like Rust, or even things like NBA, how are you going to ensure? Because back when I started off from college, I was in Cisco.
Right.
Exactly the same kind of issues when you had very small budgets, be it code in high-speed caches or the amount of cycles you have. How do you ensure this when you go to Rust?
So I don't know very much about Rust, and I think it's just up and coming. And Rust is gaining popularity among programmers because it's very fast. And we're trying to bring it into the networking platform. So that's why this number that, we get, so on the y-axis, it's the mega packets per second, the 2 mega packets per second using DPDK. So this is only 10G, and we're getting not only 70%. So we even haven't tried 40G, 80G. We're just doing single line rate. Yeah, so we're still far from very high speed, but single line rate.
Ask a quick question. So one main reason to move to software is, of course, that you save cost and other things. But another benefit of software could be doing things which are just not possible. New type of processing. And is there a good example from your experience or maybe in the community where by having a software router, we could do things which were not possible otherwise?
The things, so, so, I mean, moving the IT infrastructure into the cloud and adding a new box. I mean, I think it's the ease of, say you want to buy I mean, it's all cutting down the time. So if you want to add a new, say, intrusion detection system to your network, okay? If your infrastructure, if your IT infrastructure is already up in the cloud, and you have all this different software intrusion detection system, and you click, and then it'll come alive as on a VM overnight. So the purchase and install and all that overhead is going to be gone. So yeah, it's dream come true. I mean, so we have we're doing a IPsec redesign in Microsoft Beijing, and it's IPsec gateway boxes you'd have separate, and then now we have them in software, and instead of having a single VM per IPsec gateway, we're consolidating and cutting down the cost big time. So I think it's big on the flexibility. Yeah.
So yeah, it's commendable that you made so much progress with speed with software processing, right? But it seems like a losing battle, right? Because network speeds are always going to keep going up. And the other reason is you don't want the CPUs to be used for network processing. You want to use them for other things like computation and so on, right? So for example, Microsoft is going with FPGAs because they can free up the CPUs for other compute, right? Do the networking there. Further, you want IPsec, then again, CPUs can't keep up. So there are all these gotchas with software. So is it just academic interest with software?
No. I think it's forever. It's a networking balancing act. So depending on the memory speed, bus speed, network interface card, there's going to be a bottleneck. Sometimes it's I/O, sometimes it's CPU. Say you have we put FPGA, and it won't do everything you want. You will split computation and put some on FPGA, and the rest you will have to do it in CPU. So the load balancing will be between FPGA and CPU. So not all the processing will have the same number of cycles that you can, ship to FPGA. So this networking balancing act is going to be like this struggle between flexibility and performance. It's going to be a long struggle, depending on whatever hardware you bring. Because hardware, they are finite, and software, you can, more flexible, you can configure differently. So I think it's going to be a long battle.
Okay, let me ask the last question myself. So I think it was a great retrospective in your own work. Mm-hmm. And now there is a lot of interest in the topic. There are a lot of programming languages like P4, CCOM has a lot of relevant workshops. Mm-hmm. So my question is, you as an expert, right? Where do you see this future of software routers going? So
right. So I think FPGA, P4, I think they're basically the same thing. So we need more cycles to do network packet processing, and CPU, multi-core CPUs are for, they're like these high-speed jet engines. They are not really designed for packet processing, but we're not going to have network and NPUs as Intel once tried. So we will. As network people, we will have to depend on commodity technology and struggle to get most performance out of any existing commodity technology. And P4, their barefoot, is like one way of commoditizing a little bit of the hardware part. That's how I understand.
Okay, let's conclude here. Thanks, Sue, again. And yeah, Ashu will give some elements to appreciation.
Quick announcement. This is tea break now.